Yeah, see, I don't know. Now I'm using my laptop to charge that. That is not going to work. So that's not close. Oh, we don't need it work.
Here's a thought.
Oh, can I still laugh? Thank you.
Let's skip the final, do encryption and Bitcoin.
That is a thought. I can give you another thought. Now, your turn. Big yawn. Yes, that works. All right. What are we doing today? Section 41. And you said I counted for covering 43, which is for Maxwell's theorem, which does not get us to encryption. Because, yeah, encryption is 44, 45, and 46. So it takes 3 sections to get encryption.
To get to encryption? Or?
No, to cover it. Encryption is 3 sections. So, well, we'll cover what we cover and then decide from there what to do. Who knows how it's going to go? Yeah, me neither. Let's see. Well, I don't need to begin with, but as soon as we cover this stuff, I will. Okay, so today we are going to be covering isomorphisms, or group isomorphisms. You've never seen an isomorphism before, so it's okay to just call it that, but there are other functions that we call that in math and other fields, so this is just specific to groups. Anyways, you remember talking about groups? Let's recap with groups. What was a group?
When it had to be closed.
Well, first off, it's a, what's the actual structure?
It's a function.
It's not a function. It has a function.
Oh, it's similar to a spaces.
It's a set and an operation, right?
Yeah.
Such that, and then we have 4 properties. Now, do we remember what an operation is?
It's function on the set.
It's a function on the set. What does it mean for it to be a function on the set? For it to be an operation on the set? What's the domain of this?
Isn't it the set crosses set?
The set crosses set. G cross G is its domain, right? It takes 2 elements out of there and spits something out. Now, since this is a group, it takes 2 elements out of there and spits out an element in there. It has to be a closed operation. That's one of the properties of being a group. So, a group is a set together with an operation on the set, such that the operation is closed as 1. What else?
It has to have the identity.
It has to have an identity element. Good.
Associative.
It has to be associative.
Every element.
And every element has an inverse. Wonderful. So you couldn't remember getting started, but you remembered the 4 properties. All right. So there you go. That's a group. Now we want to compare groups to each other. And we want to know if groups are somehow the same or if groups are somehow different. For those of you taking topology, just like we have homeomorphisms with topological spaces, 2 topological spaces being homeomorphic to each other, we're going to now have groups and groups being isomorphic to each other, somehow the same. For those of you not in topology, this is similar to congruence in geometry. What do we mean when we say that 2 triangles are congruent? We mean that they're somehow the same. They're not identical triangles, right? I can have one here, they're completely separate triangles, yet they're somehow the same, and so we call them congruent. Similarly, we're going to have 2 groups that aren't identical, they're different groups, but they're somehow going to be the same. We're going to define what exactly we mean by those groups somehow being the same, and we're going to call them, 2 groups are the same, isomorphic. And we show that they're the same by finding an isomorphism, for those of you in topology, just like the way that we show that 2 topological spaces are homeomorphic is we find a homeomorphism.
Why are the names switched like that? What?
They mean different things.
Okay, this doesn't make sense to me.
It's just a name, definition. Okay, so let's jump into it, see an example, and then give the definitions, and then start answering questions. So here's the example I want to give you. I want to give you 2 groups here. We have Z4 with plus. We good with what this group is? And then Z5 star with times. What are the elements in here?
0, 1, 2, 3, 4.
Not 0, just 1, 2, 3, and 4. What are all the elements in Z5? It's all the elements that are relatively prime with 5. It's all the elements who have a GCD of 1 with 5
I didn't see the star.
from 0 to 4. So this is 1, 2, 3, 4. This over here is 0, 1, 2, 3. You good with what this set is and what this set is? And notice that they have the same size. And then you know how to plus and you know how to times, right?
Yeah.
So I just created 2 tables here, one table for this and one table for this. So here's all the elements in there, 0, 1, 2, 3. I just created a plus table. Okay? Just filled out the table, nothing weird there, 3 plus 3 is 2, right?
Yep.
You remember how we're doing that?
Yeah.
3 plus 3 is 6. What's the remainder of 6? Or what's 6 mod 4? 2. Okay. So that's our plus table. And over here we have our times table on this group. This set only has the numbers 1, 2, 3, and 4. I wrote them in a weird order here. You'll see why in a second. It's just to help you see the picture. The fact that I wrote them in a different order doesn't matter. It's still the same table. So 1 times 1 is 1. 2 times 2 is 4. 4 times 4 is 1. 4 times 4 is 16. Mod 5 is 1. 3 times 3 is 9. Mod 5 is 4. Feel like you understand this table and you understand this table? Okay. So now here's what I'm going to do. I'm going to create a function f that maps 0 to 1, 1 to 2, 2 to 4, and 3 to 3. And it's a function, notice, from this set 0, 1, 2, 3 to this set 1, 2, 4, 3. Maps 0 to 1, 1 to 2, 2 to 4, 3 to 3. It's a function from this set to this set. You see that? Turns out this function right here is going to be an isomorphism. This is my function for showing that these 2 groups are actually the same group. So notice that when we do this assignment, these 2 tables actually give us the exact same thing. So let's do that with a different color really quick. We're going to map 0 to 1. I'm just going to write it on one of these tables, doesn't matter which one I do it with. But 0 goes to 1. What does 1 go to? 2. What does 2 go to? 4. What does 3 go to? 3, etc. If I kept filling out that mapping, I'd end up with this exact table over here. So this function right here basically maps this table to this table. And notice that the function is 1 to 1 and on 2.
Yeah.
So these groups somehow have the exact same structure. Does that make sense? I take this group, run it through the function, I'm going to end up with this group. Make sense? Okay. So here's what I was saying to note up there. Notice that a plus b is equal to f of a times f of b. That's exactly what we were doing. If we do 2 plus 1, that's 3, right? So when we did 2 plus 1, we got 3, so we're talking about this one. Now let's look at f of 2. What's f of 2? That's 4. What's f of 1? That's 2. What's f of 1 times f of 2? 3. They give me the same thing. A plus b is equal to f of a times f of b. Good?
Yeah.
Okay, so that's the structure of the second. Now here's a more generic way we can write out that table. This is the exact same as this, is the exact same as this. We say, look, pick any set like this you want where E is your identity element, and pick any operation you want that does this assignment. Is this plus, is this times, is it, who knows, who cares? No one cares. This could be any operation. This could be any set of objects as long as this is an identity element and this operation does this with them. Notice what's our identity element over here?
0.
0. And where do we have zeros? We got a 0 there, 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 and there. What's our identity element here? 1. Where do we got ones? There, 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 and there. What's our identity element here? E. E, 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 E. If I map E to 1, A to 2, B to 4, C to 3, I get this table. And it turns out that that operation is the exact same thing as times on those. If I map it this way, then it turns out the operation is the exact same as plus. So you see how this is somehow the structure of these two different groups?
Then aren't they all isomorphisms?
No. For example, if I would have switched this to Z6, then it would definitely not be the case anymore. Even if I switch this to 5.
So even if they were
Why
the
would
same
that
size.
be?
What are the elements of Z6? You have 1.
2.
Nope.
Oh.
5.
Oh, because
5.
Okay, sorry.
There you go. That's your full set. And the operation doesn't necessarily have to operate the same way on them either. Just because they have the same size of set doesn't mean the operation is somehow the same. We just picked two where it happened to be the same. We're actually very lucky that the operation map these the same. That will most of the time not be the case. So just because the size of the sets are the same doesn't guarantee anything. So this is a very contrived example to show you a very specific case of where it happened to work and they happen to be the same. That make sense? Okay. And so that's what we mean when two groups are isomorphic. They have the same structure. Good? Alright, so let's actually get definitions down. So let G dot and H star be groups, and let F be a function from G to H, and let F from G to H be a bijection. So it's a bijective function. Remember what a bijection is? 1-to-1 and on 2. What does it mean for a function to be 1-to-1?
Means
That is
1
inverse
element.
is also a function.
The inverse is also a function, is one way to think about it. How else?
And 1 element maps to only 1 element.
One input maps to one and only one output. Or every output has a unique input. It's probably an easier way to say it. I can't have 2 maps to 6 and 5 maps to 6. Every output comes from one and only one input. In order for it to be on or 1-to-1, what does it mean for it to be on 2?
It uses up all of that set.
It uses up all of the, I can't remember what we call it in this class, codomain.
I think it's total.
Well, I think the range are the actual elements that we use. So if the image of the, usually we say the image, if the image is the entire codomain, then it's on 2. So a bijection maps this entire set to this entire set in a 1-to-1 way. Right? Okay. So let F be a bijection from G to H. Notice that those are the sets that we're defining groups on. Then F is an isomorphism. Notice the function is what we call an isomorphism. We call the groups isomorphic. The function that maps one to the other is called an isomorphism. Right? Isomorphism, talking about the function. Isomorphic, talking about the relationship between the groups. Okay. So then F is an isomorphism, provided that for any 2 elements in G you pick, A dot G is the same thing as F of A star F of B. A dot B is equal to F of A star F of B, just like what we did up here. A plus B is equal to F of A times F of B. So this is the operation on the codomain, and this is the operation on the domains group. Does that make sense? Okay. When there exists an isomorphism between 2 groups, G and H, then we say that G is isomorphic to H. And we write it G congruent to H. Same symbol we use for congruence in geometry, same symbol we use for homeomorphic in topology. Good? Yeah. It's our way of saying they're somehow the same. Now, let's note really quick that this is a congruence, an equivalence relation. Why do I want to say congruence relation? This is an equivalence relation. Do you remember what an equivalence relation is?
It's symmetric.
Symmetric, associative. No, not associative. That's not a property of relations.
Yeah, it's
Symmetric, transitive, and reflexive. Yeah. Reflexive. So first off, let's just think about it. Is this relation reflexive? Does every group have the same structure as itself? Yes. What's the mapping you could use to prove it?
X goes to like it goes to itself.
The identity map, right? The identity function. What terminology do we normally use? X goes to X. Just map everything to itself. There you go. That's 1 to 1. That's on 2. That maps everything from this group to everything in this group.
yeah.
And that maps this thing's table to this thing's table. That one's pretty trivial, right? What about symmetric? Is it going to be symmetric?
Yeah.
Because it's a bijection.
Because it's a bijection, so what's our function going to be?
I don't. You're talking about
What is the isomorphism that we would use to show that this isomorphic relation is symmetric? If I know that G is isomorphic to H, how do I know that H is isomorphic to G? How would I show that?
You just take the inverse of.
Just the inverse function. Since G is isomorphic to H, then there exists an isomorphism from G to H, and so its inverse, the inverse of a bijection, still a bijection, right? And the inverse is going to map the other way, and it's going to maintain this property going backwards. Where was it? Right here. Right? Okay, and then transitive, that was pretty simple. If I have one from G to H, and I have one from H to I, then you just compose the two together. Composition of a bijection, still bijection, and then this, just having a middleman step to some other operation isn't going to change anything, right? So, pretty simple. I think you're going to have to prove those on your homework, so I just wanted to go over it in a high level first, and then now you're ready to prove it, right? Piece of cake? Thinking about it? Guess we'll see. All right. Now, there was also something very special about these two groups that we used in our example here. And what you should know about these groups is this. If I take 1, what do I get? I just get 1. But what about when I take 1 plus 1? I get 2. What about 1 plus 1 plus 1? I get 3. What about 1 plus 1 plus 1 plus 1? I get 0. So notice, by plussing 1, I can generate every element in here. This is back to Z4. Let's put these back. This is Z4. This is Z5. So notice that I can use 1 and just keep adding 1s to generate every element in this set. Notice that is not the case if I would have chosen, for example, 2. I would have gotten 2, and then 0, then 2, then 0, then 2, then 0. Right? So it's not necessarily the case that I can pick any element out of here and keep adding it with itself a bunch of times and generate every element. That's a very special thing when it happens. So that happened to be the case with 1 in this set. And notice that happens to be the case with 2 in this set. 2 is just 2. 2 times 2 is 4. 2 times 2 times 2 is 8. Mod 5 is 3. Right? And then 3 times 2 is 6. Mod 5 is 1. And then 1 times 2 gets us back to 2. Make sense? So, 1 in this set is doing something special, and, well, in that group, and 2 in this group is doing something special. It's generating all the elements as we keep applying the operator to it again and again with itself. So something special is happening there. So let G dot be a group. An element, little g and big G, is called a generator, provided that every element in big G can be expressed in terms of little g, and the inverse of little g with the dot operator. So 1 here was a generator for this group. Because pick any element in there you want, I could eventually get it by adding 1's together. Over here, pick any element in this group, 2 is a generator. How? Pick any element you want, I can eventually multiply 2 by itself enough times to get the element you chose. Let's look on another set. Let's look at Z, the entire set Z, with regular plus. So there's a group. Regular addition on the integers. With me so far?
Yeah.
Is there a generator in that group?
Mm-hmm.
There's a number I can keep adding to itself and generate anything?
No.
What is that number?
1.
1?
Negative.
Generate negative 2 from 1.
Oh, because it's not the naturals.
Oh, I thought you saw it.
I did.
How do you do it? We said with G and G inverse. What's G inverse of 1 in this group? Negative 1. Can I, by adding 1s and negative 1s, generate any integer?
Yeah.
Yeah, so it works. So 1 is a generator.
Do you have to use the inverse because you didn't in your example?
So here's the gotcha. Why do we put the inverse in there? For infinite sets. If you have a group with an infinite set, you might need the inverse. When you have it on a finite set, a group on a finite set, you never need to use the inverse and you can just use G. So we just use G up here, we never use its inverse. We just use G here, we never use its inverse. We just use 2, we never use 2's inverse. We just use 1, we never use 1's inverse. Turns out if the group is finite, you only need to use G to generate everything. You don't have to use G inverse. And we're going to prove that.
What if I go from negative 5 to 5 in the integers? What number are you adding to get all of those?
Negative 5 to 5 in the integers isn't going to give you a group.
Oh, because it has to be a group.
That's okay, I see.
Yeah. So it has to be a group. If the group is finite and it has a generator, then you can get its inverse from just adding it enough times. You don't need to use the inverse to generate elements. You can just use G and generate any element. You don't need G inverse. You only need G inverse, potentially, if it's an infinite group.
So every group has this generator, right?
Now, if a group has a generator,
Then it has these properties.
then it has these properties. So this is what a generator is. We picked 2 examples that happen to have generators. Not every group has a generator.
How do you know whether it has a generator or not?
If you can do this with it. If you can generate all its elements from one element.
Yeah, but how do you do that with like an infinite set?
Well, you do it with the integers.
Yeah, but that's just an easy one.
You just think about it.
Okay.
Oh, okay.
Explain to a kid how you knew 1 in the integers.
I just thought there was a way that you would prove it, but I guess not.
So let's continue with the definition here. Let's just restart now that we've had some conversation. So let G dot be a group. An element, little g and big G, is called a generator, provided that every element in big G can be expressed in terms of little g and little g inverse with the dot operator. A group with a generator is called cyclic. So we have a special name for groups with generators in there. We call them cyclic groups. And cyclic because that generator is going to generate all the elements and then do it again, and then do it again, and then do it again. Notice if I kept adding 1s to this, I would just have restarted. And I'd keep going down this list over and over again. If I kept multiplying by 2, we got all the way to 1. Now multiply that by 2. What's 1 times 2? 2 times 2, 4 times 2, 3 times 2, 1 times 2, 2. And we just keep cycling through.
What if it's an infinite group? Can you still call it cyclic?
Yes. So the integers with addition is cyclic.
Yeah. Okay.
I was just giving intuition for cyclic.
That's perfect.
Okay. Because yeah, the actual definition is right there. That's what needs to be cyclic. But with finite groups, it's very intuitive why.
Yeah.
Okay. So, no, if G is finite, oh, we don't need G inverse to generate all the elements. We already had that conversation. Notation. Okay, you're used to G to the n means G times G times G times G, right? We're going to be using it different now. G to the n means G operator, G operator, G operator, G for any operator.
Okay.
So if we were talking about in addition here, then 1 to the 4 is equal to 0. Because that's 1 plus 1 plus 1 plus 1. Over here, 1 to the 4 is equal to 1. Because that's 1 times 1 times 1 times 1. So this notation, this exponent notation here, power script notation I should say, is not necessarily talking about multiplication.
Wait,
Do not
I'm
be confused
confused.
that we're
Are you
using
saying-
dots. This is not times. This is any operator.
Are you saying in that group? Put it in that group.
Yes, in the context of this group, 1 to the 4 is 0. In the context of this group, 1 to the 4 is 1. So we're not talking about multiplication on the real numbers. We're talking about some operation on some set in a group. Don't get confused by that. Make sense? Okay. So notation, and we're going to be using it from here on out. And let's see what we're proving. So let G dot be a finite group, and let little g be a big G. Oh, yeah, then there exists some positive integer such that if I apply that operator to G that many times, I'll eventually get to inverse. How does that work?
Yeah. What?
Can you use
I
those
don't
examples to
understand
show
what
us?
you're
Yeah.
Yeah, okay, let's come over here. So here's a finite group. Let's see. What's the inverse of 3?
It's
1.
Oh, wait, we need to pick our, well, it doesn't matter what element we pick. We can pick any element we want out there. So pick any element you want in here.
2.
0, 1, 2, or 3. You pick 2. So now what this is saying is, there is some number that I can raise 2 to the power of using it this way, not multiplication. There's some positive number I can raise 2 to the power of to get 2's inverse. So what is 2's inverse here? 2. 2 is its own inverse. So when I raise it to the 1, I'm done. So that one happened to be easy. Let's pick a different one. 3. 3. What's 3's inverse? 1. So there better be some amount of times I can add 3 to itself to get back to 1. So what's 3 plus 3? 6,
Plus 2.
which is 2, plus 3, 1, right?
Oh, okay.
So just to confirm, 3 to the 3 on that set is
3 to the 3 is equal to 1. 3 to the 3 is equal to 3's inverse. For any element you pick, we chose 3. There's some number of times you can apply the operation to 3 over and over again to generate its inverse. Over here, we chose 3, and we showed that you can add 3 to itself 3 times and get its inverse.
Can you do that with like just plain addition?
Can we do that with just plain addition? Has to be finite. But let's do another example just to, let's look at this one now to make sure it makes sense. Pick an element in here. 3 again. What's 3's inverse? 2. So there better be some number here I can raise 3 to such that it's equal to 2. Because that's its inverse. There better be some number I could put there such that 3 to that number gives me 2. So let's see. What's 3 times 3?
4. 9. Oh.
3 times 3 is 9.
Sorry.
Mod 5 is
I said addition.
4, that's not 2. So now what's 4 times 3? We're going to multiply by 3 again. 4 times 3 is 12. 12 modified is 2. So 3 to the 3 equals 2. So there was some number, namely 3.
Wasn't it 3 to the 3 last time that equaled these numbers?
Yes.
We're on
Is that
because
just
we're
going to
gonna
be
be
the
the
same
same.
pattern with isomorphisms?
It's going to be a number less than the size of this set for the first time. It repeats. It's also going to be the 7. Wait, is that necessarily true? Let's see.
Should be true.
2 times 3 is 6. Inverse is 1.
Times 3.
And then 1 times 3 gets us back. So let's see. We had 3. 3 times 3 was 4. So when we did 2 times, we got 4. When we did it 3 times, we got 2. When we do it 4 times, we get 1. 5 times. Okay, duh. Yeah, 1 plus 4 gets you back where you started. Okay, which is 5. Anyways, doesn't matter. The point is, there was some number we could raise that to the power of to get its inverse, right? This is g to the n equal to g inverse. We found the n such that this was the case. You picked any g you want, and then we found the n that gave us g inverse. We're proving that you can always do that. Does that make sense?
Yeah.
All right, so let's prove it. Okay, so since g is finite, the sequence g to the 1, g to the 2, g to the 3, etc., off to infinity. We're talking about sequence. The sequence has infinite terms in it. This sequence, g to the 1, g to the 2, g to the 3, etc., eventually repeats. This can't generate infinitely many different things, since this is a finite set.
What do you mean it'll repeat though? So you say it'll reach an end and then it'll start back again?
It will have, there will be some number that shows up twice. Maybe more times, but at least twice.
How does that make sense?
Doesn't necessarily mean it repeats.
I don't mean repeats as in has a pattern that keeps repeating.
Oh, okay.
I mean that there is some value that will come up more than once.
Alright.
That's all I mean.
Why would some value come up more than once?
So this is a sequence. So this is going to have infinite terms in it. Every term in here has to be inside of G. G is a finite set.
Oh, okay.
I can't pick the numbers between 1 and 10 infinitely many times and end up with infinitely many different numbers. I'm going to have to pick 1 or some number twice. Does that make sense now?
Yeah.
Okay. So since G is finite, the sequence, G to the 1, G to the 2, G to the 3, etc., must repeat at some point. Not have a pattern, but just the same value shows up twice. At some point, we've got to get a value that we've already seen before. That's all we're saying. So we're going to let A and B be the first indices where the sequence repeats, where it gave us the same values. So maybe that was at G to the 1 and G to the 4.
What are
Indices? Oh, that's its location. This is the first one. This is the second one. This is the third one. So its index is 1, its index is 2, its index is 3.
Okay.
That's all I mean by that. Okay. So let A and B be the first indices where the sequence repeats, and assume that A was the one that came first out of the two. So eventually we get two values. Say that happened at spot A and spot B. Maybe that was at 3 and 27. So A would have been 3 and B would have been 27.
These are both repeated numbers.
This is, yeah, the first time that we saw a number come up twice. So we got some sequence, and it gave us 1, 5, 9, 13, 5. Oh, we've seen that one before. Stop. Here's my A, here's my B. A's 2, it's where that one happened. 3, 4, 5, don't get confused. The index and 5 are the same thing. Here's my A, here's my B, right? That's all we're saying. So, let A and B be the first indices where the sequence repeats and assume that A was the first of the two. So in other words, we're saying G to the A equals G to the B.
Yeah.
You with me on that? The 8th term is g to the a. The first term is g to the 1. The third term is g to the 3. The 27th term is g to the 27. The 8th term is g to the a. The bth term is g to the b. Nothing weird there, right? Okay. Eighth. A-T-H. Oh, not 8, the number. Do we need to use X and Y so it doesn't sound weird? I think you understand what I'm saying now, right?
Yeah.
Okay. Yeah, we were not saying the number 8. We were saying a term. The term at position A is g to the a. The term at position B is g to the b. And we're saying that this is the first time we're seeing the same number twice. So those two numbers are equal. They're the same number. So g to the a equals g to the b. Okay. Assume by way of contradiction that a is not equal to 1. What we're saying is, when you continue in the sequence, the first time you get a repeat, it's for sure going to be the number 1, whatever you started with. I'm not going to get 2 5s before I get another 1. And I'm going to show that real quick. So assume by way of contradiction that...
Why do you always get first number 1 repeated?
Not number 1, but whatever your first term was. If when I do the sequence...
Why would your first term be the first thing repeated?
We'll show real quick. Assume by way of contradiction that it's possible for it to not be the first term repeated.
Okay.
Let's see what happens. Well, then g to the a equals g to the b. Right? We know that since it's a group, g has an inverse element. So, apply the operation to both sides. Should get the same value, right? That's just a rule of logic.
Yeah.
And now, g inverse, well, rewrite this really quick. Pull one of the g's out. So this was g to the a. Since g to the a is not 1, then it's greater than 1. So I can pull one of those out. Right?
G to the a is not 1, so it's greater than 1.
Yeah. Because it's an index. 1, 2, 3, 4, etc. So it has to have been at least 2.
Okay.
Okay. So I pull one of those terms out, so now we only have a minus 1 left. And I pull one out from here, so now we only have b minus 1 left. You with me? And then I realize I skipped a step. Sorry. What is g inverse dot g?
It's just 1.
Not 1.
Next to the other?
The identity
Oh,
element.
yeah.
Yep.
Could be 0, could be 1, could be e. It's just the identity element. So this gives us the identity element, this gives us the identity element. And then the identity element dot g, a minus 1, is just g to the a minus 1. And the identity element dot g to the b minus 1 is just g to the b minus 1. So now we got g to the a minus 1 is equal to g to the b minus 1. Repeating index, or repeating values, right? Contradiction, because we said the first repeating values are at a and b. Those numbers are before those numbers, and that's a repeating value, which doesn't work. So that gives us that a minus 1 and b minus 1 are repeating indices. Contradiction. A and b are my first repeating indices. A minus 1 and b minus 1 are earlier indices, and they're repeating. Contradiction. We can't have that. Make sense? Therefore, a has to be 1. So whatever value repeats first, it's whatever value you start with. Make sense? Okay. Now, the next part of this is to prove that we can eventually get g inverse. Don't forget where we're going. We need to find an n such that g to the n gives me g inverse. That's where we're trying to get. So now we know that a is equal to 1. So since a is equal to 1, then g to the a equals g to the b is the same thing as g to the 1 is equal to g to the b, right? A is equal to 1. Or g is equal to g to the b, in case you didn't know what to do with g to the 1. It's tricky. Thought I'd show you that step. Okay. So now, I'm going to apply g inverse twice to both sides. Apply g inverse twice to g, and apply g inverse twice to g to the b. We didn't change anything, right? Still equal. Did the same thing to both sides. Well, inverse dot G is just the identity element, right? And then, wow, I skipped a lot. I don't know why I wrote the identity element one way and I didn't write two identity elements here. Let me just write it right instead of trying to over-explain. So this is going to be, we're going to get G inverse dot the identity element. From this one, those two together give me the identity element. I'm going to pull two G's out of here and combine them with these two to get two identity elements. So this is going to be equal to identity element dot identity element. Maybe I don't even want to skip that far ahead. Let me just write it this way. We'll just get rid of this and rewrite all this out. It's worth seeing
Or
over
say
here.
it's the identity dot identity.
Yeah, but we got to be careful because we only have associativity. We don't have commutativity. So we got to be
Right.
careful that we don't use that.
Oh, because it's a group.
It's a group.
Okay.
So that's why I want to write out the algebra here a little bit. So G inverse dot, I'm going to pull two G's out of here. G inverse dot G dot G dot G to the B minus 2. You with me so far?
Yeah.
Okay. So now, that gives us that. This one we're fine with, right? And that can just go G inverse, not E inverse. G inverse, when we dot that with E, nothing tricky there, right? So this is going to be equal to, when we put those two together, we get E. Because of associativity, we can apply the operation. We can basically put parentheses right here into this one first if we want, right? We can put the parentheses however we want. We can't change the order of the terms, but we can put the parentheses wherever we want. That's associativity, right?
Yeah.
So I'm going to put my parentheses right here to start with and do that one first. So this is G inverse dot E dot G dot G to the B minus 2. With me there? Now I can put parentheses, doesn't matter which way, but I'll just put it like that. We'll do that with our parentheses now, which just gives us G, exactly G inverse dot G to the B minus 2. And we'll put our parentheses there now, which gives us E dot G to the B minus 2, which then applying that gives us G to the B minus 2. So it works exactly the way that you always thought it did. Like there was nothing weird there. We knew B, we knew we could just add the exponents, B minus 2. That still works the same way we expected, but I want you to understand that all we're using is associativity here. Does that make sense?
Yeah.
Okay.
So
So we're done.
that B minus
What?
2 is the end.
B minus 2 is the number.
And when B is the first repeating term.
Where G to the B is the first time we see G again.
Yeah.
Then back two elements is going to be G inverse.
How do we know there's even that many elements back?
Back two elements is going to be G inverse.
What if,
What?
what if it's a really small finite group but only has like 2 or 3 elements?
If it has 3, we're fine. If it has 2, did we ever talk about G to 0? G to 0 is always just identity element.
Right.
So if it's only a 2 element set, then we always get identity.
Which makes sense, does that?
Let me make sure I didn't do anything wrong. It may be the case that B is equal to 2, so G to the 2 is equal to G. so he took the time to take one more note that we didn't take yet. And he noted that g to the b minus 1 is going to be the identity element. So let's see where that would be the easiest to see. So come back and look at right here. I have that g is equal to g to the b, right?
Yeah.
So that gives me that g inverse dot g is equal to g inverse dot g to the b, right? Which gives me that identity is equal to g to the b minus 1.
Okay. You said G inverse is the identity?
So
G
g
inverse
to the
of
b
G.
minus 1 is the identity element, always. So then, if we have the special case where b is equal to 2, so let's see, if b is equal to 2, we have g is equal to g to the 2, like that. Which means that g to the 1 is equal to 2 minus 1, which means identity is equal to g to the 2 minus 1, which means it's just identity.
Okay.
So the repeating element, whatever it is always just going to be identity in a 2-element set. So that's what I think. Let me read his little note here. We now know that if we stop at the first repeat, the sequence is, no, okay, notice since g is equal to g to the b, if we operate on the left by g inverse, we get identity is equal to g to the b minus 1, we said that. It may be the case that b is equal to 2, so g squared is just equal to g. In this case, g is equal to the identity, and so g to the 1 is equal to g inverse, proving the result. G to the 1 is g inverse. G to the negative 1. When you subtract 2, then it's just g inverse. Oh, it's its own inverse. Okay. So in this case, notice that when we do b to the minus 2, if b's 2, then minus 2 gives us the inverse, right? Oh, which will just give us back identity because it'll be g to the 0. Okay, that's going to make sense. But then in general, if b is greater than 2, this is our result. Now, this is our result. G inverse is that. So b minus 2 is the number. But I said n a positive integer. Maybe I just say natural. Maybe read the start one more time, see if I miss that. And then for some positive integer n, that is the case. G to the n is equal to g inverse. Oh, because if it is the identity element, so in the case where b is 2, in that special case, then it's just the identity element, and so g to the 1 is equal to g inverse, because it's an identity element. There we go, now it makes sense. So this formula doesn't give it to us when b is equal to 2. In that special case, the element is its own identity element, and so 1's the magic number. When b is greater than 2, then this is the number.
Okay.
Okay, so that takes care of it. That's a lot more clear. Good question. Okay, so our next proof. A G star being a finite cycle.
Do we need to move the camera?
Yes, we need to move the camera. Thank you. finite cyclic group. Then G dot is isomorphic to Zn with plus where n is equal to the size of G. Okay, so here's a pretty cool theorem. Let's make sure that this makes sense what we're saying here. Pick any group that you want, and all you know is two properties about it. Property 1, it's a cyclic group, has a generator. Well, any finite group you want, we know it has a generator in there. And we know that however many elements are in G, we're going to call that n. Look at the size of G, that's n. Then we're saying, plug that n in here and give this modular arithmetic addition, and you get the exact same group, or an isomorphic group. So every cyclic group, every finite cyclic group is going to be homeomorphic to some group like this, where n here is the size of G. Does that make sense? So, clear back over here, our first example with the times. Since 2 was a generator, we knew that this group was cyclic. And since its size was the same as the size of Z4, then we knew that these two were going to be isomorphic, and we didn't need to find the function now. So we're going to show that all you need is, this basically gives us one group that we can always show that they're the same as. And so it's like a middleman group to show that two very different groups are actually the same. So it might be hard to show that group A is somehow the same as group B, but maybe I can show that they both have a generator in them, and show that they both have the same size. Therefore, they're both the same as this group. Therefore, they're the same as each other. That's the type of logic that you could use there. So just knowing that a group has a generator gives you a ton of information about the group, if it's finite. Okay. Does that make sense?
Your example didn't, because Z sub 5 star, its size isn't equal to 4.
It is.
It was just 1.
C sub 5 is 1, 2, 3, 4.
I don't know, I just think it's something similar.
But now we do know that if it has a generator, we'd have to check if it has a generator, but if something like Z sub 1974 star, if there's a generator in there, then we know that this is going to be isomorphic to its size of this same set over here. As long as it has a generator. And we don't have to limit ourselves to think about times and these things for any group we find. Alright. So let's prove this. So 1, let G dot be a finite group, finite cyclic group, comma, and let n equal the size of the set G, whatever it is. And let, we want to grab its generator element, so let little g in G be its generator. So since I know that G is cyclic, it has to have a generator element, call it little g. And then it's finite, so whatever its size is, we're going to call it n. Good?
Yeah.
Alright, so now we need to find a, we're trying to show, we're trying to show that G star is homeomorphic, not homeomorphic, don't let me say that, isomorphic, my symbol's fine, jeez, is isomorphic to z sub n plus, right? This is what we're trying to show, where this n here is the size of g. That's what we need to show. Now, how are we going to show that? How do you show that two groups are isomorphic? You need to find an isomorphism. I need to find a function from g to zn such that, or maybe I want to go from zn to g, doesn't matter which way I go. Let's see which way he goes. That'll probably be easier to follow him. He goes from zn to g. Yeah, I suspected. So I'm going to find a function that goes this way. It doesn't matter which way. I'm going to find a function that matches zn to g, maps zn to g. It needs to be 1 to 1. It needs to be on 2. And I need to show that it has this property. That a dot b is equal to, let's see, which one are we starting with? We're starting with the plus. I need to show that a plus b is equal to f of a dot f of b. That's what I need to show. So I need f like that, and I need to show that a plus b is equal to f of a dot f of b. So I need to find a function that has this property that's 1 to 1 and on 2. With me?
Yeah.
All right. 2. So now let f from g, not g, we want to start in zn. Let f from zn to g by f of, these are the numbers 0 through n. Yeah, not including n. So 0, 1, 2, 3, all the way up to n minus 1. So what should we call those elements? Little I? Or should we use a little m? That might be a good one. F of m, whatever's in here, is equal to g to the m. Where g, we already have g. G is a what? A generator. So I'm guaranteed that this generates all the elements in G.
Yeah.
Why would that be equal to each other?
That's how I'm defining my function. This is my definition of my function.
So
I am going to
f
call
of m.
f of 0 g to the 0. I'm going to call f of 1 g to the 1. I didn't prove that this function has the properties we want to have yet. This, it just turns out, is going to be my isomorphism. And I need to prove that it has all the properties we want to have.
How did you, like, what was your thinking behind choosing that as your isomorphism?
This will eventually generate every element. It's a generator.
I know, but you said
So it's going to be 1 to 1 and on 2. This is going to be bijection right out the door.
and you just know that it's going to satisfy that property.
Satisfied. Oh, well, the only reason I know it is because I was asked to prove it. I would not have in a vacuum assume that those two things are isomorphic. But then if you come along and you tell me, hey, show that these things are isomorphic, this is about as natural a mapping as you can come up with. It is not intuitive to me that this maintains this property. Like that doesn't just filter my intuition. If that's what you're asking.
It is. Okay. Alright.
But this is the most natural mapping of this set to this set.
Right.
See, it's the only way that you can think to even try it to have a chance at being a bijection. Okay. So, first thing we need to do is show that this thing is, well, it doesn't matter which one we do first. What do you want to prove first? On to or 1 to 1? 1 to 1? Did you guys say opposite things?
Yeah.
1 to 1. Okay. So we need to grab two things out of, we're mapping this way. Let me draw this in a different order so I don't get confused. So I want to go left or right. I want to go like this. here is Zn, and this is plus. Over here we have capital G and dot. Okay, so what do I need to do to show that a function is one-to-one? I need to show that if I grab two elements out of here that are the same, then they came from the same element over here. How do you show one-to-one? In general, you show that f of A equal to f of B implies A is equal to B.
Yeah.
I already know this way is true by definition of a function. It's a function if A equaling B implies f of A is equal to f of B. That way it shows it's a function. This way it shows it's a one-to-one function. If the output's the same, the inputs have better been the same. Does that make intuitive sense?
Yeah.
This is what we're trying to prove when we're trying to show one-to-one. So I need to grab two things out of there, and I don't know what to call them. Let H and I, is that okay?
Yeah.
Let H, I, and G such that H is equal to I. Now that gives me that there exists, maybe we won't call them H and, I don't know, will I be skipping too much? I don't want you so many letters, I confuse you. So maybe you'll be okay with this. Since we know G's a generator, then let G to the I and H to the I be any two elements in G. Since, oops, G to the H, except for I want HI. Let's be alphabetical here. Okay. Since any element in G can be represented as G to some power, little g to some power. Little g is a generator, right? So any element in big G can be represented as little g to some power. So I can grab two random elements out of big G, and just because I express them this way does not mean that they're not random elements. We still know nothing about those except for that they're in here. So are you okay with me calling them random elements like that?
Yeah.
And you understand why that's valid? I'm not cheating. This is just two random elements out of there. We could have called them big, let's use big letters, and that way I think we won't get confused. So then when we get rid of them, we'll be okay. So let A be in G. Now notice that since they're in G, they can be generated by the generator. So that means that there exists HI such that, I need to specify that very cool. Sorry. So let A be in G such that A is equal to B. That gives me that there exists H, comma, I in the positive integers such that A is equal to G to the H and B is equal to G to the I. And now we'll ignore the big A and big B from here on out. I just didn't want to use a ton of letters and get you all confused. Grab two random elements in G that are equal. Since they're in G, they have to be able to be generated by the generator. So there has to be some H I can raise G to get A, and there has to be some I I can raise G to get B. So now G to the H is equal to G to the I. Maybe put that last line here, last bit of logic. So I now know G to the H is equal to G to the I. Good?
Yeah.
Okay. Now, I need to use this to show that this is true. So I need to show that H is equal to I. How am I going to do this?
Wouldn't you just use the thing that you let right there on your second row?
Let f be a function from Zn to G by that.
So G of H is equal to F of H.
Yeah, but I don't know that the H is in here. Because H and I can be absolutely massive numbers right now.
You do know what's in there. Because they're in the positive integers, right?
They're positive integers.
But But
the
they might
n
not
here
like
could be
it.
10. This could be 10,952. This could be 26,297,141. Who knows?
Yeah.
Yeah. So I need to get them down. So I could subtract I from each of them. I don't know where I'm going with this yet. I'm just playing with it. So that gives me that g to the 0 is equal to g to the I minus h. Right? If I apply g inverse h times to both sides,
That makes sense.
then we get that, which gives me that my identity element is equal to g to the I minus h.
Wait a minute.
I don't know that I like where this is going.
Apply G inverse H to the what?
If I apply g inverse h times, then that would give me this and this,
Oh.
or identity. Sorry, I'm just thinking ahead to try and figure out how I'm going to do this. Let's see if he starts with onto, or yeah, maybe starting with onto will somehow help us. Nope, he starts with 1, 1. All right, let's see how he does it. Let's not get stuck on this forever. Suppose f of j is equal to f of k. Oh, what am I doing? I need to pick a and b out of the domain, and then show that if f of a is equal to f of b, then a is equal to b. How did you guys let me do this? You're terrible.
I was.
All right. Let
Makes sense.
h I n z n such that f of h is equal to f of I. There we go. Now I've got h and I in the domain. That's the whole thing I was struggling to figure out how to do. Okay. Way easier. Well, that gives me, just write an implication out, that gives me g to the h is equal to g to the I. Right?
Yeah.
Okay, so now I know that my h and I are in Zn. Now I need to show that h is equal to I. We want to prove that j is equal to k. Suppose that j is not equal to k. Without loss of generality, we can assume that j and k are both less than n. Yes. Alright, so let's continue down that road and see where that gets us. 4. Assume, by way of contradiction, that h is not equal to I. That gives us that. And we'll just, one of those numbers is going to be smaller than the other, right? If h is not equal to I, one's bigger, one's smaller. So that gives me that 0 is less than or equal to, we'll call whichever is smaller the two h.
Okay.
Right? Doesn't matter. If we accidentally had this one bigger than this one, just relabel it. Call the smaller one h, the bigger one I. So assume by way of contradiction that h is not equal to I, then we know that 0 is less than or equal to h is less than I is less than n. How do I know that both h and I are less than n?
Because it's inside G. Because it's inside Zn.
Because they're inside Zn. Remember, h and I are in Zn. And what is Zn? It's all the integers from 0 to n minus 1. So it doesn't include n. All right. We can dot the equation g to the oh, we're going to contradict g being a generator. Okay. Assume by way of contradiction that h is not equal to I, which gives us that. we're basically going to say the identity element is equal to g to the I minus h, where I minus h is less than n, but it's also less than n minus 1. Let's see. Here's what the author is essentially saying. I'm just trying to come up with a better way to say it. Maybe you'll just get it by saying the way the author says it. The author is saying, look, the identity element, first off, that's g to the 0. And it is repeating in I minus h steps. Well, I still don't like the way they're saying it. I'll tell you exactly what they're saying. They're saying, since we use I and h, since I minus h is less than n, this means that the sequence g to the 1, g to the 2, g to the 3, etc. repeats after k minus j steps, and therefore g does not generate the entire group, but only k minus, or I minus h elements. However, g is a generator, which is a contradiction. So that's what they're saying. I
So
don't
basically
love
proving
that.
that it doesn't generate the whole set.
Because I minus h is less than, I want to say it's less than n minus 1. I think this is a better way to see it. Because the difference between those has to be at least 1.
What if h is 0 though?
What if h is 0, I is still less than n?
I
And
could be
greater than.
n minus 1, right?
It could be n minus 1.
Which means I.
Oh, less than or equal to. Okay, so less than n is still fine. Yeah, I was thinking less than or equal to. Good. Good catch. So less than. Okay. That works too. Which gives me that I minus h plus 1 is less than or equal to n. Do I still want to say it that way? Still don't like that. E is equal to g to the I minus h, where I minus h is less than or equal to n. But then when you plus 1, it could be n. Because he's saying this means that gives us that the sequence g to the 1, g to the 2, etc. repeats in I minus h steps.
Because it's equal to the identity.
Oh, okay. No, he's right. It does repeat in that many steps. Why? Because that many steps is identity. So I start with g, then in this many steps, I would have applied identity to g, which is g again. Okay, now let's look. Let me say that again.
Yeah.
When I do g, I minus h times, let's recall this. E is equal to g to the, we'll say, little a, where a is less than n. Just so we don't have to keep saying I minus h so much. So that means that this sequence repeats in a steps. Why does it repeat in a steps? Because when I apply g a times, that's the same as applying the identity. So I start out with some term. Then when I apply g a times that term, I'm back to g. Because g to the a is identity.
Yeah.
So my sequence repeats in a steps, not n. A is less than n. So I can't generate all n elements because my sequence is repeating after we only generate A elements.
Okay, I see what you're getting at, but
So that
why
gives
does
us
that prove that?
that G is not a generator. Contradiction. By definition, we said G is the generator. G is a generator by definition. So it has to take G n steps to repeat. It has to generate all the elements before it repeats. Right? Here we're saying, look, G is going to repeat in A steps.
How do you know that though? How do you know?
G to the A is equal to identity.
You just said that though. How did you prove that?
Oh, sorry. Let's come back up here. Okay. Is that what you're missing? Okay.
Yeah.
So yeah, we're gonna apply H. We're gonna apply G inverse H times to both sides of this. Apply G inverse H times to both sides of this. That gives us this. Obviously, that gives us identity. Now we assume by way of contradiction that I and H are not the same number. We'll call H the smaller of the two. So then identity is equal to I minus H, where I minus H is less than n. So in I minus H steps, we applied identity. So take G, now apply to G itself, I minus H times, we're back to G.
Okay.
So if we are repeating G in less than n steps, then we're not going to generate all n elements. We're only going to generate I minus H elements. So G is not a generator. But by definition, G is a generator. Contradiction.
Gotcha.
All right. There's our one-to-one. Now let's see our on-to. Okay, 6. So, to show it's onto, we need to pick something in here and show that we can find something in here that maps to it. You with me?
Yeah.
So, 6. Now we'll pick something in there. I don't know. A be any element in G. Let A be any element in G. I need to find something in here, in Zn, such that f of Zn gives me that A. To show that's onto. With me? Let G and A, or that slanted. 6. Or let A in G. Well, since G has a generator, I'm guaranteed that there must. That gives me that. That wasn't the right way to say this. I'll just say it this way. There must exist some I different from whatever i's we use up there, such that G to the I is equal to A, since G is a generator. Furthermore, we know that G repeats in n steps, so it generates all the elements in the first n steps. That's the other part that I'm trying to figure out how to say in words. So here's what I'm basically justifying, where 0 less than or equal to I is less than n, or we could have done greater than 0 and done less than or equal to n. G is a generator, it repeats in n steps. Right? It generates all the elements and then repeats and repeats and repeats. So we're guaranteed to get all the elements between 0 and n, inclusive on the 0 or inclusive on the n. Doesn't matter which way we go. But in n iterations, we're guaranteed that we got all the elements. Just to make this very clear, I could have also said between 2n less than or equal to I less than 3n. We're saying in n iterations, we're guaranteed to have gotten everything. Doesn't matter which n we pick. I could have also said 2n plus 3 to 3n plus 3. And it's still true. Pick any interval of n elements I want. I'm guaranteed that that has all of them. In this sequence, sorry. In the sequence, I guess we said there, G2, G3, dot, dot, dot. Eventually we get Gn, Gn plus 1. And it keeps going, right? Here's our sequence. Pick any starting index and ending index that covers n iterations of this thing, and we're guaranteed to have all our elements. Because this thing is cyclic.
Yeah.
Does that make sense? Okay, so here's an interval that covers n. So I'm guaranteed that in that interval, we would have gotten that value somewhere in there. Does that make sense?
So you have a sequence, and this
This
sequence
sequence.
is
Yes.
going to go up to n, and then it's going to start repeating. You're saying wherever n amount of number you pick, then you will find an a in that
Yes.
finite set.
It will print out. So, for example, when we were doing it over here, we got 2 to the 1 is this, 2 to the 2, 2 to the 3, 2 to the 4. And then 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8. So if I were to just write out the sequence, we've got 2, 4, 3, 1. 2, 4, 3, 1. Our number is n, right? I'm saying pick any interval that has n elements in it, that has 4 elements in it, and you're guaranteed to get all the numbers. So I could have started right here and went to the next 4. That gave me those 4. I could have also gone back 1 and started with 2 to the 0. What would 2 to the 0 be in this case? 1. I could have also picked these 4.
Right.
So as long as we're grabbing n consecutive terms in the sequence, we're guaranteed to get all of them. So we're going to grab the first n, starting at 0. Okay. And then obviously that I is going to be our 7. Then I is in Zn, and f of I is equal to g of I, or is equal to that a. So it's on 2. Now we need to show our last property. So we need to show if we grab 2 elements in there, huh?
I'm confused how you do that. How f of I is equal to 8. Okay.
You see it now?
Yeah.
Grab some random a. We're guaranteed that in this interval, since it has n elements, we generate that a somewhere at some index I. Well, that I is going to be in Zn, and now f of I gives us a. So we found some number in Zn such that f of Zn gives us that a. Good?
Yeah.
All right. Now, lastly, we need to show that if I grab 2 things out of Zn and add them together, and add them together, that's going to be the same thing as this. Let's see how that works. Okay, 8. And I guess I'll just use little a and little b for this to help us remember that we're using that. Let a be in Zn, that f of a dot f of b is equal to g to the a dot g to the b, which is going to equal to g to the a plus b. Right there. I think I'm supposed to do f of what I plug in gives me what I get out. I wonder if I wrote that wrong. Yeah. Jeez. Can't believe I had that wrong this whole time. Where is our definition of a group? We need to map this thing. Oh my goodness. F of a dot b is equal to f of a star f of b. Yeah. I can't believe I didn't write that. Yeah, that would be really weird otherwise. F of a dot b is equal to f of a star f of b. So f of a plus b, and that's even what we were doing over here when we said this. We said map this thing. F of a plus b is equal to f of a times f of b. I can't believe I did that.
That makes so much more sense because I was looking at the table and I wasn't working it out.
Yeah, so looking back at the table, you take a plus b, you map it, and 3 went to 3 over here. Let's pick one that didn't. You map this one and you get this one. Okay, yeah, you need to map it. It needs to go through the function. You can't just not use a function. I can't believe I had that. Terrible, terrible. F of a plus b, better be that. Okay, that's what we need to show. So we know that f of a dot f of b is just g to the a plus b.
How do you know it's g to the a plus b?
That's f of a dot f of b. We still need to show that
Yeah.
f of a plus b is equal to g to the a plus b.
How do you get g to the a plus b?
Let's see where you're lost. I see you're good going from here to here.
Yeah. There.
Here we have ga times. Here we have gb times.
Yeah.
So total I have g a plus b times. If here I have g twice and here I have g twice, total I have g 4 times.
Okay. Yeah, that makes sense.
Okay. So now f of a plus b is equal to f of a plus b mod n, right? Now, this is going to be the same thing as we're saying we want the remainder when we take this and we divide it by this. So do some scratch work over here real quick in case you don't remember doing this all the time. So if we are doing a plus b mod n, we're saying the remainder when we take this and divide it by this. So when we do this divided by this, we get a plus b is equal to some integer k times n plus r, where r is the remainder. This is the remainder, so that's the same thing as a plus b minus k times n for some integer k. Now, since I'm going to pick an arbitrary integer, I'm going to use plus over there, because it can just be the negative of the one we talked about over here. So this is equal to f of a plus b plus some integer times n. You follow the logic there? What is this k? It's the negative of whatever this k was. So this is equal to g to the a dot, well, g to the a plus b plus k to the n. Right? Since G is a generator, G is equal to G to the n plus 1. We got to apply n to G. We got to apply G. We've got to apply G to G n times to get back where we started. We have to go through n rotations to repeat. We repeat every n rotations. So if G comes up on 1, it's also going to come up, maybe if I put a 1 there, that will help it make more sense. If I got G on 1, I'm also going to get G on n plus 1, and on 2n plus 1, etc. Does that make sense? So G to the 1 is equal to G to the n plus 1, which gives me that the identity is equal to G to the n. Does that make sense? I just did G inverse of both sides. Good? Okay, so now notice that we have k n's here. All those are going to turn out to be identity. That's where we're going with this. Then G to the a plus b plus kn, we'll try and spell out the algebra a little bit here, is equal to G to the a plus b times G to the kn, right? Which is equal to G to the a plus b dot G to the n k times. Maybe you'll be okay with that.
Which is just E k times.
Wonderful. Which is just G to the a plus b times E k times, which is equal to G to the a plus b, which is what we were after.
Yep.
Because we already showed right at the beginning that's f of a plus f of b, or f of a dot f of b. Good? Okay, that's it. So that's the end of that section. I don't know why I thought we'd do 2 sections today. No way. So we'll call it there for today, and next time we'll do subgroups.
So we're not doing section 42 today?
No.
Does that mean we need to do the section 42 homework?
Eventually.